Hello, this is a video presentation comprised of discussion and example of tree and data structure. Here on the right is an example of a tree, a binary tree of that is. And next slide. We already tackled about linked list queues in the previous video. We discussed about its type, function, application on um, making codes. We discuss its advantages and disadvantages when using it. Today we're going to talk about trees in data structure. Trees is somewhat similar to linked list but differs in function. A node in a linked list can only link to only one node, but in tree a node can link to multiple nodes. Take note of the word children. In data structure, we use this term to identify the hierarchy of the data. We will further discuss about the later. Um, we discuss about that later on in understanding important terms. And let's do a little recap on our previous video about linked lists. Here is an example of single linked list, and on the bottom right is a code which a class which I named node and has an int data number, int number data, and node next which um, access data in a single direction. Well, on the double linked list we have a node code. We can access data backwards and forward. In tree data structure, it has a different appearance as well as algorithm. It's a bit complex compared to the linked list, but it serves as useful as linked lists or even better. Next slide is gonna studied. You can identify the terms to know in tree data structure. These few words you keep it in order to understand structured data. A structure of the structure of data on the tree. You can search for other fundamental terms used in tree, but keep these terms important. Now we have the root, which is the level 0 of the tree. There can only be one root per tree, and a root has no parent node and can only have a child node. Well, in binary, a root can have a maximum of 2 children. A parent node, any node except the root that has another node connecting to it. A parent node can also be a child node, and on child it is a node connected to a previous node, and leaf, a node which has no child, and we have here traversing, passing through nodes in an order. Next slide, we're gonna identify to further visualize. We have here a picture of a tree data structure, and the root connected to the arrow, which is the first. It's like a pyramid, or we can say it's like an inverted tree. It's like tree or puno inverted, and we have here the parent, the child, and here the child is also a leaf node, like. And for wait, this here is considered a subtree of the root or the tree. Also this, consider a subtree of this node. So here I have wrote a code, pseudocode. I have a class. I name it node2 and data. In here, this is a binary tree. Here is the node left and the node right. Um, to fully visualize my explanation of this, think of it as your family with you as the child node, and your parents are the parent node. Your family is called the descendant of your grandfather, or we say the root, or or this node, meaning to say your family is a subfamily of your grandfather, and that cycle will continue on until you, the child node, will become a parent node. For example, this is you, and when you grow older, you'll have a family, you have child. For example, two child, or you can only have a maximum of two children. If you have, if you refer to it in a binary tree, but you can also have many children. I hope your father will also be happy with that. And after you have a child and your parents become grandfather and grandmother nodes, happy family. Next is types of binary trees. We have a strict binary tree. Each node must have only two or no children. The full binary tree, each node has exactly two children and all are of the same level. And here is on the middle tree, that is the full binary tree. Complete binary tree, all levels are completely filled except for the last level, and must start from the left in sequence. Remember this term very well. Next one, binary search tree. Binary search tree has a special condition, whereas the left node must not be greater than of its parent node, while the right node value must not exceed its parent's node value. And there are also operations that can be performed on the BST, or the binary search tree. We have the insert. Inserting data in a tree, or if no data is present in a tree, it creates a tree instead. Search is simply searching the data from the tree. In order traversal, the left subtree is visited first, then the root, and later the right subtree. This is a ascending order. Pre-order traversal, the root node is visited first, then the left subtree at the right. This is the descending order. And the post, it's somewhat descending order. But after the root, you're gonna left, you're gonna go right. It's like an acute angle facing right. And the post order traversal, the left subtree is visited first, then the right, the last is the root node. Don't get confused with post order traversal and in order traversal, because in order traversal is the root node is the last visited node, while in order traversal, the right subtree is the last visited. I have written a pseudocode for search and insert operation right here. In insert operation, if root is empty, like I said a while ago, it create a root, which is the data given by the user. if root exists, that's supposed to be else root exists, else compare user data to node value. This and while loop, while using while loop until user data is inserted. If user data is greater than the node value, insert to the right. Like I said a while ago, if the inserted data is supposed to be is greater value than the root, or any node that of the yeah that the user data is inserted to the right of the node. If user data is less than the root node or the node value, insert to the left until everything is satisfied, until the user data has been inserted. It's gonna end the while loop. And in search operation, if search data is equal to is equivalent to the root value, return the root value of that or that node value, or else while data not found, if search data is greater than node value, go to the right of the node and search there. Else if search data is less than node value, go to the left of the root node. You're gonna search the value there. Else data not found. If kung wala na, if kung sinesearch mo yung wala, you can put a warning there. It's like data not found or error. And after that, the while loop will end. Next, we're gonna move on to another tree, that is the Adelson-Velsky-Landis tree, or the AVL tree. In PowerPoint, I see no about the AVL tree, but I'm gonna discuss this here. If I'm not, correct me if I'm wrong, I didn't see it in the PowerPoint, or just missed it. AVL tree, this is a balancing binary search tree. Well, it falls in the category of the binary search tree, but with an additional property. That difference of height between subtrees left and right, it can be more, and it cannot be more than 1. Here, the height of the two subtrees of any node has a difference of at most 1. The difference is called the balance factor. This here is a balance. Right here is a balance tree, while this one this is descending order. It's an ascending order. It's supposed to be 2 here. It's supposed to be 2, not equals to 0. And also this one, 2. How can I write here? Oh my gosh. Oh, you get it? So these are not balanced because the balance factor is equal to 2. Now I want you to search about the AVL rotations. AVL tree rotates in order to balance itself. That is what we call AVL rotations. Consider this as an assignment for you and study those rotations. Next, we have generic tree, the NRA tree. NRA tree, or in other terms, a generic tree, can have at most n number of children, and the n must not be a negative number. It must be 0 or greater than 0. In this tree, it is not possible to give each a name, each node a name. For example, left node, right node. Therefore, we need an array to store the children. For example, here, there's only one root on this tree and it has 3 children, which in turn have different number of children too. So in here, we must construct an array to store the children. So that will become easier to traverse. And for the assignment, um, oops, identification. We have three for identification. This is equal to 7 points. Next, we have the identify the AVL3. If balanced or not, this is equal to 3 points. And we have enumeration, 1 to 3 types of binary trees, 4 to 8 BST, basic operations, 9 to 10 important terms to know in tree. And overall, we have 20 items. And they search for different kinds of AVL rotations. I didn't discuss the XOR and the Q or the remaining discussions because I think it's hard for sixth grader to comprehend those terms. I just discussed the most basics of the tree and what terms to understand in order to construct a tree and the pseudocode, and that's all. We're gonna end the discussion here. I hope you understand quite a few things in making trees and the parts of trees, and I'm gonna see you on the next video.